In this lecture, we developed the product rule. We want to develop a number of major rules for derivatives. The product rule is the first one. It's the first rule that at first glance does not appear to be natural, and so we must learn it consciously. The product rule may be motivated by the rate of growth of a rectangle, or we can work it out algebraically. Suppose we wish to take the derivative of a product of two functions. For example, one function might be f of x equals x squared, and the other function might be g of x equals sine x, so that I'm looking at x squared times sine x. I know how to differentiate x squared. I know how to differentiate sine x. How do I differentiate x squared sine x? By the definition of the derivative of a product is going to be this limit. It's f of g evaluated at x plus h minus f of g evaluated at x, which by the meaning of the product of two functions is really this. F of g at x plus h is the same as f at x plus h times g at x plus h. So I get these two terms here. And then f of g at x, fg at x is f of x times g of x. So we're involving this product. A little bit of smart algebra helps here. We're going to put into this expression a 0 written this way. We're going to write 0 as minus f of x plus h times g of x plus f of x plus h times g of x. Turns out that this works real well because it allows us to break up my numerator into two nice pieces. So here is my formula for the derivative of a product. First, we have f of x plus h times g of x plus h minus f of x plus h g of x. And then on the other hand, we have this expression, and we've added in these two terms in the middle so that we can break things up this way. Now I can factor f of x plus h out of the first expression and factor g of x out of the second. And so what I've got is this expression. Began with that expression. I created this one. Now, as I do this, I'm taking a limit, and here the limit involves h. There should be an h down here. That's an error. There's a typo. Should be an h. And here's an h. Here's another limit. These pieces right in here are derivatives. So what I have is the limit as h goes to 0 of f of x plus h times the derivative, plus the limit as h goes to 0, the derivative of g of x. And so when I break this up, I'm going to get the first expression. As h goes to 0, I just get f of x. This expression is g prime. So I get f of x times g prime. And then in the second term, I have f prime times g. So because I was able to break this up into two pieces, in one case I get f of x times g prime. The other case I get f prime times g. So my answer is the derivative is f of x times g prime plus f prime of g of x. What does this really tell us? If we're going to differentiate a product, we do this by taking the derivative of one expression times the other term, undifferentiated, and then adding an expression in which the roles of the derivative is reversed, writing down the undifferentiated term times the derivative of the other. For example, the derivative of x squared sine x will involve the derivative of x squared, which is 2x, and the derivative of sine x, which is cosine x, but we have to put them together in the right way. The derivative of x squared sine x is 2x sine x plus x squared cosine x. In the first case, 2x is the derivative of x squared. We just wrote down sine x. Then we wrote down x squared and took the derivative of sine x. We can better understand the product rule if we view the product as representing the area of a rectangle. If f of x is the width of my rectangle, here I have a rectangle down below, f of x is this width, and g of x is the length, so g of x is the length across here, then the area of my rectangle is width times length, f of x times g of x. Now what happens if x changes a little bit? How does the rectangle grow? If my width grows by a little bit, up here is going to be delta f, change in f, and then my length grows by a little bit. So on the right we have a slightly longer rectangle. Then the area of the rectangle grows a little bit. It grows essentially by this quantity. Approximately the two blue rectangles represent the increase in area. So if I think of a product as area, then as the two pieces grow, what is added on? What is added on is this blue strip here along the top, this vertical blue strip on the right, and a very small little gray rectangle that turns out not to be significant. Again, as x grows, my product grows by two major pieces, change in f times g, change in g times f, and a small piece that ends up going to 0. So the change in the area is roughly change in f times g plus f times change in g. If I divide by delta x and take a limit, I have the change in f over x, that's the derivative of f in the limit, and the change in g over x, that's the derivative of g in the limit. So I have the derivative of f with respect to x times g plus f times the derivative of g. Again, the sum of the two pieces here can be explained geometrically by the light blue rectangles up here. All right, so the derivative of those two pieces, the derivative of product is the derivative of f with respect to x times g plus f times the derivative of g. The notation I've used here with the df over dx, where the derivative of y with respect to x is dy dx. This was introduced by Leibniz over 3 centuries ago and is often called Leibniz's notation. If instead we use our prime notation, the product rule says this: the derivative of fg is f prime g plus fg prime. How do we take the derivative of a product of more than two functions? Suppose I have a product of three functions. I'm multiplying x squared times x cubed plus 3x times sine x. We just follow the pattern that's been set before. You pick a function and differentiate it. Multiply that derivative by the undifferentiated pieces. Then pick another function to differentiate and multiply that derivative by the undifferentiated pieces. And continue this way until each function has had its turn being differentiated and multiplied by the others, and you add up the expressions. For example, if I want to differentiate x squared times x cubed plus 3x times sine x, then I differentiate x squared, getting 2x, and I write down the others. Then I differentiate x cubed plus 3x, getting 3x squared plus 3, and I write down the others. Finally, I differentiate sine x, getting cosine x, and I write down the others. And then I put them all together. So if you want the derivative of this, you add up those three pieces. In the next presentation, we will develop the quotient rule.